So we just talked about how sediments and hillslope material and soils of any kind can move downslope, and how when we combine this slope related or gradient related downslope transport function with a conservation function, we end up getting a diffusion equation. And that diffusion equation has a classic form where there's a first derivative in time being proportional to a second derivative in space. But material moving downslope is not the only thing that happens on hill slopes. And one of the major ways in which other material can be eroded from hill slopes or deposited on them is by the wind. And this acts as a local, what we call source or sink term. And what do I mean by that? What I mean is that a source is where there's something incoming, so this is going to be a positive, and a sink is where we're taking something away, and so that's going to be a negative term. And so you can think of source terms in this case being specifically deposition, and sink terms being erosion. And so what are a few real mechanisms that we can think of by which the wind might create source or sink terms? So, for example, we can have deposition. Whoop. Wow. Go computer go. All right. So deposition of things like sand. And so you can have dunes. And so you can think about something like you might have in map view, some of these sorts of dunes marching across the landscape. And perhaps some like sheets of sand in between them. You can also think about loess. So this is going to be loess here, which is silt material. And this is just going to create kind of larger, thick deposits. So silt creates loess deposits. And this is going to be looking in cross section. So right here, we're looking at Z being up. Here, we're going to look at Z being up this way. And so here we have something like, let's say that this is an old, these are just my little root casts. This is an old soil surface, so paleosol. Ooh boy, my spelling is not good right now. Paleosol, there we go. And then this can be a whole package of this silty lussic sediment sitting on top of it. And there can also be erosion. I'm going to put erosion over here. And so if you imagine that there are these sand sheets, then maybe the wind comes in and blows all of that sand away. So, bye, dunes. And that could happen if, for example, in the source area, we have trees and plants, so vegetation of any kind, holding soils together. So that means that there is not very much coming in, but there's still material moving out. So similarly to our argument about sand moving downhill. You can also have erosion occur if you have a surface that maybe has some sort of like rocky bump in it, right? And so there are going to be all these sand grains swirling and bumping in the wind. And then, oh, I'm sorry, they just bump into this rock, and then they, hit this rock again, and eventually, over time, some chunk chips off. It might be extremely tiny. It might just be this little tiny abraded itty-bitty piece, but still that piece is breaking off of this rocky outcrop, and eventually it forms what we call benefacts. And these are wind erosion features, and eventually there can be some significant Aeolian erosion. And so this erosion is going to be taking stuff away, and this deposition is going to be adding material. So if we think back up to this, this box that we drew, so we had a box here on the hillside, and this was going from x naught to x naught plus delta x, and there is some sort of rate of Aeolian deposition. And I have this downwards arrow because I'm saying that it is positive when there's extra deposition, which is going to cause this box itself to grow. And so we really want to call it positive if the box gets bigger. So we have a box whose width is delta x, so going from x naught to x naught plus delta x. And so I'm going to go through a very trivial integral. But just in case it's been a little while since some of you have done integrals, we'll just have this be a nice practice round. So we have this thing right here, which is a delta x, where a is this rate of Aeolian deposition positive or erosion negative. And we're evaluating it between x naught on the left-hand side and x naught plus delta x. So there's not a whole lot to do, so then we just turn it into this evaluation of the definite integral, right? And this term here is going to equal a times, since we just have x here, so a times x naught plus delta x minus a times x naught. Right, and this ax naught term there cancels with that one right there, and so we just get a delta x as our solution. And so what that means is that the rate at which extra material is being added is related to the width of this box, and the rate at which there's deposition. What we might be worried about, though, or might be considering if we're trying to figure out what's happening in a hill slope, is the rate of vertical elevation change due to Aeolian processes. And we're going to call this z dot a. And so just as a quick key, if there's d over dt of, let's call it squiggle, that is going to be equal to, by definition, ooh, can I make the same squiggle? Oh, that's pretty good. That squiggle with a dot on top of it. And so this just means rate of change of squiggle, or whatever thing that is. There we go. Ooh, can I? Yes. Wait, no. There we go. All right, I'm getting the hang of this tablet, I promise you guys. Just keep getting digital ink blots everywhere. So, now, if we think about that then, the rate of the Aeolian erosion and deposition, if we have that box again, we have A going down there, and this box is delta x wide, and so we have A delta x being added. Divide that by delta x, and we just get A. All right, we could have told you that from the get-go, right? We just have a deposition rate A. Fine, we did some integrals. Now you guys are like hopefully a little bit warmed up, a little bit more used to it, which is good because the integrals are going to get harder. So after this, but don't worry, the integrals don't get harder until after the Aeolian section of hill slopes. So after this, what we're going to define is just say, we're going to say that there's something called z dot a. And this means that, as we set up there, that this is the rate of elevation change from Aeolian deposition. And so if that just equals A, the next thing I'm going to do is I'm going to redefine this z dot from up above, and we're going to call it z dot q, where that signifies the portion of the change in mobile material column thickness that is due to downslope transport of hillslope material. And so if we want to know what's happening in this whole column, we can just sum the Aeolian component with the lateral transport component, or the hillslope creep component. And that's what we get here. So this is then hillslope creep plus Aeolian processes. And so what you can see then is that the Aeolian processes in this equation create what we call a source or sink term. And that's when you have this constant where it can be a positive, which it makes it a source, or a negative, which makes it a sink. And that can then arbitrarily affect based on however we, from some external knowledge source, know the Aeolian processes are occurring, can externally affect the change in thickness of the Hillslope material, or in this case, elevation of the surface over time.